I have to say, it's both an honor and a pleasure to be in this role, particularly following in the footsteps of some very formidable meeting chairs. I'm looking at several of them that are here tonight over the years. So I take it pretty seriously, and I'm hoping to rise to the same level that they set. So they set a pretty high bar for me, and I'm hoping I can keep to that standard here. So we've got a terrific agenda tonight. So I worked, some of you may know, I worked a lot on this with a number of you here. In addition to our usual features, Gary Boyle on Ottawa skies, and Al Scott on the astronomy news, current astronomy news. We've got two speakers that came from out of town, and I'm really delighted with that. There's Normand Fulm, who is here. Many of you know, he's garnered much praise for his fine telescope, very specialized telescope making skills. He's got a presentation on that tonight. One sample, by the way, is in front of me, in front of the podium. And Mike Earle, many of you may remember Mike Earle from the very animated meeting chair. I found him and I brought him back, and I had a really nice dinner with him tonight. And he's going to, his passion for satellites and tracking satellites, well, guess what? He's still into it. So that's, and you'll hear that tonight. I've seen both presentations. You're in for a treat, okay? Janet Tulloch, she went recently to California. She's got a great presentation as well on something that she witnessed at the Griffiths Observatory. You'll like that as well, I certainly do. A couple of program notes, door prizes. I'm moving that to the very end of the, thank you. I'm moving that to the very end of the meeting. Okay, so you can collect the tickets for the door prizes in the break, but we're going to actually run the raffle at the end of the meeting itself. Once the meeting closes, and I did that intentionally, just to be less disruptive to the folks on the internet, and really focus on the speakers. Okay, we'll see how that goes. If I get feedback that that's not the way to do it, we'll change. Okay. The other thing I'd like to do too, to respect the folks that are joining the meeting through the internet, is that if there are questions raised to the speakers, I'd like to ask the speakers if they don't mind repeating the questions for the benefit of those folks that can't hear or are calling through the internet. So you might see me jump in from time to time just to repeat the question again for those folks. So I apologize for interrupting in advance. Okay, so let's, before we get started, I wanted to have a quick preamble of, and I have to say that as I was preparing for this meeting here, there's quite a bit of work that is put into this meeting prior, in preparation, collecting slides, speaking to people, trying to find out, what would work and so forth. Lots of emails, follow up. Chris does a huge amount of work, and I'm very impressed by that. But then it kind of hit me as a revelation that what do I do during this meeting? Okay, and because as I see, Eric is doing tons of heavy lifting. Chris is doing the same with the slides. So perhaps in the interest of streamlining this meeting, just maybe going forward, that you don't need to see me. Now work with me for a second on this one here. Maybe you can see something in place of me that might be more satisfying. All right, and so I need your help here, and I need the help of the folks that are on the internet too. So what I'd like you to do here is, over the next couple of slides, I'm going to show you some various graphical images. Okay, that can serve in place of the meeting chair. Okay, avatars if you like, And what I'd like you to do is sort of vote for your favorite graphic representation of the meeting chair. And it's the same thing with you folks, calling in through the internet. And you can clap, you can roar or whatever, but and you can also vote more than once. Okay, so here we go. Okay, so who is this? Cary Grant, obviously a real charmer in his time, and it sounds like there's a few takers there as someone who could possibly be a substitute for me, at least visually. Next up is George Clooney, okay, of Mare 11. Ocean 11. Oh, that's the same thing. SEAL. But Very attractive fellow, obviously, if you're into good-looking men. Tom Cruise, not my favorite, but I thought he might appeal to the younger crowd. Some people might find him very desirable, and he's certainly endowed with many features. Okay.
It's so you, Mike. No wonders if she's in the right meeting.
Okay, so Raquel Welch, obviously endowed with some features as well. And it sounds like you'd rather look at her than me. But by the way, this photo was taken 1 million years ago, so I've been assured by Chris there's been no photoshopping that's been done on this photo. Okay? And by the way, I have to tell you that assembling the slide pack was a real labor of love. So, anyhow, I should be careful here because our Eric, our videographer, is going to want to, who records and streams this presentation live on the internet, is going to want to introduce a 6-second delay to edit out any indiscretions from me. So we can't have that. Okay, so judging from the response of the group tonight, it sounds like it's not me. but you're very generous. I was thinking if it was going to be rock silence or dead silence, I was going to say, well, clearly the silent majority hasn't spoken, but some people have. Thank you for that. Let's move on. All I can say is that I'm really looking forward to the next 2 years. This is going to be a lot of fun. I'm hoping to make this journey an enlightening one for you, one that you'll enjoy as much as I think I will as well. And I really hope that you. I'm trying to make this your meeting that you'll like. So let's move on. We're here. So we got a bunch of new members here. Is there any one of these folks, Ken, Scott, Al, Diane, Jeff, Gerald, Maxwell, and MD in the audience tonight? I think I saw Alan, right? Yeah. Alan, welcome. It's good to have you here. At the break, we're going to show a slide which shows the benefits, okay, of membership. So, and we'll leave that slide on during the course of the break. But it's really terrific to have you here. Thanks for coming, and thanks for joining. Okay, some sad news. Come out, please, Rob. One of our members, longtime members, passed away recently, and Rob Dick, who knew him well, will speak to it.
Okay. Well, good evening. Some of you may remember this fellow as, this is a terrible picture of him. Really, it's a terrible picture. He didn't look anything like that. However, you might remember him as being the guy in the far, not with Isabel up there, but another person in a wheelchair in the far, your right-hand corner, and that was John Knight, Dr. John Knight. And I've taught at university for many, many years, part-time, and it's one thing to remember it as the old scraggly guy that always gave you F's and so on, but it's something else to be remembered as a really good teacher, and he was one of my best teachers I've ever had. So that's my memory of John, and that he actually was a really remarkable teacher. He had quirks that which made you want to go to class to see what the heck is this guy going to do or say this time. And so it just continued, and then it disappeared after I graduated, and then only to find him starting to come to our meetings a number of years ago. So for most of you, you didn't really meet him very well, didn't really speak to him, but he was a very knowledgeable fellow, and it saved me from some pitfalls of, so as an engineer, I come up with great ideas until I'm told why they're not. And he's very blunt about telling me when something was not such a good idea. And that's but the way he said it was also very endearing as well. And I just sorry to see that his passing, but I think for some of you who have seen him here for the last few years, you've seen them slowly going downhill. And so he's had a very long, full life and a very respected life at the university, retiring a number of years ago. Even though he retired many years ago, he's one of those people that never really retires until they need his office. So then of course he retires for good then. But I'm very glad to have seen him show up at some of these meetings and having some talks with him, especially so many years after I graduated, and I'm a white hair. So I'm very sorry to see him passing. I hope there'll be more in this crowd that will take his take his place in terms of being mentors and conversationalists as well after the meetings and even before the meetings. So sorry to see him go, but we'll try to keep his memory alive.
Thanks, Rob. Those are very nice words. So, members of the news, maybe I'll let you do it, Chris. Next slide. So, again, please, Chris.
Sky News.
So, in Sky News, there was a couple of things that were noteworthy recently. Peter Cervolo, who I think most of you know, he and Deborah moved recently to the British Columbia, the BC interior, the southern British Columbia. So you're starting to see some photos here, the one on the top left, of Orion and the Pleiades, and that he took recently. And this says here this was taken 3,000 feet above sea level. So nice to see that contribution. Another one that surprised us was Shane Finnegan of Ottawa. Shane, are you here tonight? Well, Shane, if you're watching us through the internet here, this is great. We found out that you are an Ottawa RAC Center member. Now we need to see more of you, Shane, sharing your slides and going forward in our meetings and so forth. So well done, but Shane, I kind of look forward to see some of your emails and your contributions in the meetings ahead. Okay, next, Chris. Okay, most of you know this annual edition from Sky and Telescope, the beautiful universe here. What you can see here is a image from our friend Mike Worth, and again from of the moon, as Mike is so famous for here, and it showed up in beautiful universe. So well done, Mike.
He's probably watching too.
Excellent. Thanks. Next slide. Okay, we're off to the monthly Ottawa skies, where Gary Boyle will talk about what's up in the Ottawa skies in this month.
Thank you all, and Happy New Year to here in the audience and you on the internet around the world. Hope you've had a good celebration during Christmas, good New Year's, and let's hope for a good 2014. So on to the first slide. Today is the peak of the quadrantid meteors. The meteor peaked actually this afternoon at 3 p.m., but the shower's still on. We're still in the stream. Did anyone get to see any of the Geminids a few weeks ago? It's pretty cold. Okay, well, I heard a voice. That's good. It was pretty cold. I did about 4 15-minute spurts. I saw about 20. A few fireballs. Even with the moon out, it was just phenomenal. And the quadrantids are something like the Geminids. They're very slow, 41 kilometers per second, and the average is about 120 per hour. So get home tonight, and it's a very late shower too. As you can see, it's below Ursa Major. So once you get home, if it's clear, bundle up and head outside. You might see a great shower because the moon will not be interfering. That's for sure. Okay, next slide, please. Jupiter that we see in the nighttime sky will be rising at sunset on the 5th because it'll be on opposition. Opposition, the people that don't know, is when you have the sun on one side and a planet or the moon exactly 180 degrees across, or from each other. So Jupiter will arise at sunset and set at sunrise. And there are many great transits of shadows and of the moon itself across Jupiter. This is through Starry Night. This is the demonstration coming up on the 4th, tomorrow, of Ganymede, how it crosses in front. And you can see that the moon is very close to the shadow because, again, the sunlight's almost lined up. But as the months go on, the shadow and moon will be a little wider apart. So if no one's ever seen this in a telescope, you really have to look at this inky black spot. And also check your observer's handbook on page 132, I think it is, for many transits. Next slide. As always, the International Space Station, which is orbiting Earth once every 90 minutes, can be seen over anywhere pretty well if you're in the right place, right time. It does come over Ottawa, sometimes in the morning, sometimes at night. So I just picked up one of the brighter displays that we'll see on January 11th. It'll be in the morning, starting at 6:22 on the southwest, and be a nice 75 degrees high. And you can see negative 3.1 magnitude, and Jupiter, as bright as Jupiter is only minus 2.8. So it's a bit brighter than Jupiter, and it moves, takes about 4 minutes to go from horizon to horizon. So unmistakably, that will be the International Space Station. So bring out your neighbors, kind of early in the morning, but still you can bet some money on it if you want and make a few bucks. Next slide. This will be the actual path that the ISS will be taking over, and you'll see that pretty well very close to Lyra, or in the constellation of Vega. So again, we'll start to see at 6:23. That's when it comes out of the Earth's shadow. And that's one thing to notice too, is when, just as the sun sets at night in the west, if you look on the east, you'll see this dark band. Well, that's actually the Earth's shadow. And same thing in the morning, as before the sun rises, you'll see the shadow coming down. So the ISS will be coming out of the shadow overhead and then actually go over the horizon on the northeast. And next slide. And for a nice digital moment, on January 24th at 4:30 in the morning, we'll have Saturn and Mars with the nice crescent moon, pretty well third-quarter moon, crescent moon in the middle. And even though it's cold, a little fact, even though it's cold today, bone-chilling cold, it's nothing compared to the moon. The unlit side of the moon is average about 150 degrees on the minus side, Celsius. And on the sunlit side, it's about 130. So really, if you're on the moon, it'd be a lot colder. But it's a dry cold. It's great. It's just wonderful. And next slide, please. And for the object to photograph this month, of course, the double cluster, which is pretty well below Cassiopeia. It's actually in Perseus. But to find the double cluster, if no one's ever seen it before, as I tell people, it takes stars 1, 2, 3, 4, and 5. Take star 3, 2, and double the distance down to the double cluster. Easily seen at a pair of binoculars. Next slide, please. But with the double cluster here, we have the Heart and Soul nebulas. Could be tricky to view in binoculars, too wide to be seen in binoculars. Photography is the only way to actually capture it, but using the double cluster as a guide is pretty well your stepping stone to these great objects. The Heart Nebula in IC 1805 is about 7,500 light years away and about 100 light years wide. And the Soul Nebula, IC 1448, is about the same dimensions and about 1,000 kilometers closer. Okay, next slide. And just pick out your favorite planet and know where to find it. As we see, the Jupiter, Venus is in the western sky. It's pretty low in the west. It's a very, very large crescent. Who has seen Venus in a telescope recently? The very large crescent. Joe Bonner, excellent. Yeah, it has these very nice phase structure because Venus is moving between the Earth and the Sun, so we get the huge phase size, but very, very thin. So we only have a few more weeks until it crosses above or below the Sun, and then we'll see it again in the morning sky. Okay, next slide. And your favorite lunar phase? We had the Wolf Moon coming up. So that's it for this month. Any questions, comments? No? Anybody thawed out yet? I'm still not thawed out. You thawed out? Great. Okay, folks, have a great month, and hopefully we'll see you at the Canada Science Tech next month. Take care.
Al Scott will give a 10-minute update on astronomy in the news.
So, new venue. This is great. So, a little bit about a recent space astronomy mission that just launched. The European Space Agency launched its star-surveying satellite Gaia into space on December 19th. Gaia is hoping to produce the most accurate three-dimensional map of the Milky Way ever, and to better understand the evolution of our galaxy. Gaia is now headed for a stable orbit around Lagrange 2, about 1.5 million kilometers away on the opposite side of the Earth from the Sun. And it's going to point away from the Sun and the Earth, and it's got a big heat shield to protect its instruments. That heat shield has deployed after launch, and it's on its way. So the mission, as far as I know, is looking good. Once it gets there later this month, the satellite's instruments will be switched on. The mission is making very precise measurements of the stars using twin telescopes. I don't know if you can actually see them here, but there's basically rectangular apertures in here. They're a pair of telescopes oriented about 120 degrees apart on this cylinder. It's studying the position, distance, movement, chemical composition, and brightness of 1 billion stars in our galaxy. Roughly 1% of the Milky Way's stars will be cataloged accurately with this mission, everything down to magnitude 20, basically. The data will help scientists determine the Milky Way's origin and evolution. This project is a successor to the Hipparcos satellite, if any of you are familiar with that one, which launched in 1989 and measured the position of 100,000 stars in the Milky Way. Where Hipparcos cataloged these stars, Gaia will survey almost 10,000 times as many at roughly 40 times higher precision. It will allow the nearest stars to have their distances measured to the extraordinary accuracy of 0.001%. Even stars near the galactic center, some 30,000 light years away, will have their distances measured to within an accuracy of 20%. Gaia will repeatedly scan the sky and observe each of the billion stars an average of 70 times over its 5-year mission. It will measure the position and key physical properties of each star, including its brightness, temperature, and chemical composition, by taking advantage of the slight change in perspective that occurs as Gaia orbits the Sun during a year, or parallax as astronomers know it. It will measure the stars' distances, and by watching them patiently over the whole mission, it will measure their motions across the sky. The motions of stars can then be put into rewind by scientists to learn more about where they came from and how the Milky Way was assembled over billions of years from the merging of smaller galaxies, and into fast forward to learn more about its ultimate fate. Give an idea, a little bit more of an idea of what this is about. So this is a blow-up of the spacecraft itself. The sun shield right here is 10 meters across, to give you a sense of the scale of this instrument. At launch, the spacecraft weighed over 2,000 kilograms, including 400 kilograms of propellant, 710 kilograms of payload, and 920 kilograms service module. The instrumentation includes 2 identical silicon carbide astrometric telescopes and imagers, and you can see them up here. This torus is actually made of silicon carbide, which is kind of like a ceramic with high thermal conductivity and high strength. So you have 2 telescopes at about 120 degrees to each other, and they're both imaging onto a detector array right there. It also has a blue and red low-resolution spectrophotometer and a radial velocity spectrometer with a resolution of about 11,500. The telescope primaries are 1.45 meters long, and they are nickel-coated silicon carbide on a big torus, as I said. They're unobscured and off-axis 3-mirror anastigmats, which will minimize diffraction and thermal effects because of the extraordinary accuracy they're trying to achieve. They're also been super polished, ion milled, to get very smooth. Together, Gaia's CCDs make the largest focal plane ever flown to space, a total of 1 billion pixels covering an area of 0.38 square meters. Gaia will perform its measurements by simultaneously observing 2 target fields onto the same array. The spacecraft will rotate around its longitudinal axis at a rate of about an arc minute per second, equivalent to a spin period of 6 hours, to scan its fields of view across the sky. To eliminate micro vibrations from a gimbaled communications antenna sending all this data down, Gaia is using custom-designed X-band phased array communications link to electronically steer its data link back to Earth. Here's the Gaia focal plane blown up to give you an idea of what, these are all CCDs, very large CCDs on the focal plane. And what happens is the image is tracking along as the spacecraft rotates. And what happens is the stars from each telescope will enter the sky mapper area here. Each telescope has 1 column blocked out, but they overlap. The fields of the 2 telescopes actually overlap. So you'll pick out stars from telescope on the left here and the telescope on the right here. And then as they come in here, they'll be both images will overlay and they'll move across this area and they'll integrate what they call time domain integration, where they move the charge on the pixels in sequence with the motion of the image so that you don't have to read it out all the time. So it allows you to get longer integrations with less readout noise. So at the end of this, they'll have very precise measurement of the position of all these stars. There's also, as I said, the blue and the red photometers, and then a radial velocity spectrometer with a big grating at the end here. Here's a picture of the focal plane array being assembled to give you a better sense of the scale of this system. I'll just go quickly through a couple more. Here's the telescope, silicon carbide telescope wrapped in multi-layer insulation in the lab. You can see the mirrors. So you have a primary up here and a primary here. Secondary on the far side. This will be a tertiary here. There'll be a tertiary below here. And then you can see a little bit of the focal plane array through that hole. Here's the 10-meter solar protection array or sun shield being unfurled. And that's the end. So thank you very much.
Al, thanks again for coming. I know you had quite a rushed trip back from Montreal, so I very much appreciate it. By the way, I'm really heartened to see just so many people that came out, ventured out on a cold night like this. So, well done, everyone. I'm hoping you enjoy it. So next up, it's Normand Fulham. It's one of the 3 special presentations we have tonight. Normand is an artisan, and you can see a sample of his work, as I said earlier, in front of us. And he's also into some very, very specialized optics, as you'll see. So please welcome Normand Fulham.
I use this to
Right.
the right one.
Yes.
OK. Alors, bonsoir tout le monde. Ça fait vraiment plaisir d'être ici avec vous ce soir. Et puis, merci Mike de m'avoir invité. Oh, sorry, nobody mentioned that it was a French presentation. No, just kidding. I'm very happy to be here tonight. It's the second time that I do a presentation for the RASC. One was in Montreal many years ago. But since then, my life changed a bit. Usually, over the years, I've been making presentation about my company. I call it my company now, but it was a project a long time ago that I had to make telescopes. And over the years, the presentation got longer and longer and longer and longer. And the last time I did my original presentation was at the Starfest last year, and it lasted over an hour and 10 minutes, I think so. I'd made a new one now. And instead of starting my presentation with the history of the company from over almost 18 years now, because everybody knows me or heard about me, about my wooden telescope and small mirror making, and my love for astronomy and observation, visual observation. So now I've decided to change my presentation and start about 3 years ago when my company got really a new horizon. Okay, I changed my horizon. So if I'm gonna start my present, there we go. This is a good reason why I'm in astronomy. Just looking at a star field like that can blow me away every time. Just thinking that one of those stars could harbor a planetary system and someone could look at me at the same time that I look at them. So it's always very inspiring for me. So here we go. Optic Fulham. Telescope Normand Fulham. Fulham telescope. It's all the same. It's me. I start my presentation here with Optic Fulham because it's the new name that I give to the company. Officially, I'm still Telescope Normand Fulham Incorporated, blah, blah, blah. So it's too long. So Optic Fulham, it's shorter and it tells whatever I do. The photo here of Saturn is very, very representative for me because it's a picture taken by a customer of mine in Australia that uses one of my new technology mirror, a 16-inch sandwich mirror that we use. Call them sandwich, but I call them Technofusion. So it's one of the first actual picture taken with my new technology. So I was very proud, and he was very happy about it too, saying that it was a very average seeing that he took the picture also. You can even see, there's a light on this?
Center.
Center? Okay. You can also see the octagonal here on the top of the Saturn. Okay. Like I say, 3 years ago, I decided to have a new orientation of the company. Wooden telescope, smaller mirrors, and good optics, it's fun to make. But as a businessman, it wasn't enough for me to keep going. I needed more project, new product also. So what I did is I did an expansion plan, a really serious one. Went to take some courses and I went to at night, and then also I built larger machines because my plan was to build. Well, actually, it wasn't my plan. It's the demand. Okay, I had to respond to the demand of my customer. They wanted bigger, larger, and better. So I had to adjust my company with that. So a larger polishing machine, a larger shop, because when I first started, I was in my basement, and then I moved to about a 600 square feet shop. And then I doubled that size, 1,200 square feet. And then I moved that shop to another place to about 15. And now I'm at about 3,200 with the new machinery that I got. So I had to move the shop. Also, I work very closely with Laval University in Quebec because one of my customer and is one of the researchers at the Laval University and is an amateur astronomer also. So we kind of joined our forces and in the new orientation. Also, we will see in the presentation that I acquired a kiln to do my own blanks, my big mirrors. So that will be something we'll go through over with. So, large polisher from scratch. Okay, all my machines I've been working with in the last 15 years are homemade, from machine that makes mirror from 4 inches up to about 36 inches. That was the machine that I had at the shop. But since the demand asked for bigger, so I had to build bigger machine. So instead of going out and buying a $150,000 machine, I asked my friend, machinist and welder, to help me out, and we built a machine to do those large telescope, the large mirror, from scratch. So we knew we needed a big plateau, and we needed a big support for the large mirror that are very heavy. So I've made a 54-point floating point cell on the machine, so the mirror is very well set on, how could I say, supported. Thank you. Is the machine almost finished? Because we don't want any torque or any deformation of the machine over a heavy weight. We had to build it out of steel, 2x4 steel, and build it on rails, so it's easy to move around in the shop, so it can be movable. There's one of the motor for the rotating table. And there's the plateau itself. Disconnect from the machine because it's good to grind and polish a mirror, but we also have to measure it. So in order to measure a mirror, the mirror has to be taken from the machine onto a table and flip at vertical and then back on the machine. So instead of just moving the mirror itself, which is kind of dangerous to break, I made the entire plateau that I can take from the machine, remove it, and put it on a table that can be tilted. There we go. So here's one of my mirror on the tilting table. As you can see, it's really well supported from underneath and from the edge. We're going to go back on the mirror itself, how it's made. Don't worry. So this is a 50-inch mirror blank on the testing bench right now. So it's safe, even if it's at the vertical, and it's easy to remove from the table and put back on the machine. There's one of my good friends here with the mirror on the machine. It's a 44-inch mirror on the machine. I don't know if anyone recognizes Mr. Pierre Tournay, very well involved into Dark Sky Association in Quebec. And the happy man here once the machine is done and working. And I have a small video showing the machine working on see, this is a 61-inch blank, and you're going to see the machine working, polishing it right now. So if I can, there it is. So we have the plateau, whoops, turns, and sorry. Oops. So you see there's a automatic drip that goes on the mirror with the liquid, the cerium oxide, and you will see a drip automatically. It's made with the photocopier motors and windshield washer pumps and stuff. It's all homemade. So you have the overarm, very heavy duty overarm to grab the tool. The second motor, you get a very good gearbox there. And you will see underneath the mirror, the support, the very good support for the mirror itself when it's on the machine. There we go. So this is all homemade. So I'm very proud of that. to make just right now, I'm going to show you another video of a very smaller version of a machine that works on different size, smaller size mirror. You will see it's the same principle, but because it's such a large piece of glass and you don't want to break it, so it has to be done very, very heavy duty. So the next one is a smaller machine that I have at the shop here working on smaller mirror. This is a 30-inch. So it's the same principle, an overarm that will grab the tools and move it around elliptically on the surface. You can control the speed, the amplitude of the movement, and the weight on the mirror, and stuff like that. This is a 30-inch, and then the next one is, you will show you the, I think it's a 14-inch or 16-inch. Look very tiny. Just a matter of perspective here. So right now I have 7 machines working in the shop, starting like I said, like 4 inches up to 61 inches. So I needed more space for my shop for a good reason here. A kiln, because I'm going to make a long story short. Okay, the big problem I had over the years to be able to enlarge my capacity of larger telescope and larger instrument was the supply of large blank, mirror blank, lightweight mirror blank. And I had an idea how to make the blank, 2 plates with columns in between, make it very lightweight and fast cooling. But the only person that were making them in those years was a guy in Val d'Or that went out of business because the skill went up in flame. And he was making them out of plate glass, which is not perfect. So in the year after that, I tried to have them made in China. I had a lot of promises, spent a lot of money, but they were never able to come up with a blank suitable for my needs. Germany, same thing, and also in the United States. So that's when me and Jeff Yang from Laval University got together, because the university was looking to buy a huge kiln for their research, and I needed a big kiln to start my own blanks, to fuse the glass together. So I offered my shop to install a large kiln because they didn't have any room in the university. So that's how we came to an understanding that I got the kiln in my shop and they can use it whenever they want. And I can use it as a, so it's a good understanding. So we had that kiln made for our need. It's 10 feet by 10 feet by 4 feet inside capacity. It's a very, very heavy duty, very well made, especially it's made in Toronto, actually. It's made in Canada, so I'm proud of that. But, like I say, it's in Toronto, it was built, so I had to ship it to my shop. So here's the kiln arriving at the shop in 2 sections. So it took about 3 weeks to assemble and have it run at the shop. So as the 2 sections coming together, The floor itself is on rail, so the lid lift with the help with a car lift, and then the floor just roll on rails out, so we can put the glasses on and then put it back, and then you see here the computer that runs the show here. I can get it as precise as a half a degree an hour difference in the rise of temperature and annealing session. So it's a very, very precise computer for the kiln. You can see inside here all those black lines, all elements. You have elements on the walls, the ceiling, and on the floor. So, and the kiln itself, when it's in use, goes up to almost 900 degrees Celsius. And the outside walls itself never get warmer than 40 degrees Celsius. So it's very well insulated. So that gets us to the Technofusion mirror blank that I made. So this is the main goal of my last 3 years' work, to be able to produce, grind, polish, and do the entire work to make a mirror of that dimension. In the past, I could promise people that I would get supplier to make them, and sometime you probably know about Orion Monster Dub that I had a contract to make over the years. That's the problem I had. That's why they pulled the plug on the project, because it took too long to get a workable blank in the telescope. But now I'm able to produce very, very fast those mirror. Just as an example, I can make a 36-inch mirror entirely finished, ready to put in a telescope within 2 months. Cut the glass, fuse it, slump it, grind it, polish it, aluminize it, and then ready to put in a scope within 2 months. So that was my goal, that I succeeded so far. So how do I make those blanks? I won't tell you all the secrets, but just like IKEA. Okay. I get some borosilicate 33, which is the equivalent of a Pyrex. It comes in sheets, okay, 15 millimeter thick. I buy that in Toronto, in Techniglass, and they ship it over to my shop. I have a company in Laval with a water jet cutter, so they can cut whatever diameter circle that I want from those huge sheets. They are about 67 inches by 93, so it's quite big sheets. Why water jet? Because it doesn't induce any heat, so the glass doesn't shatter. So it makes a very clean cut. So Laval University helped me out also on the design and where to put the post to build those mirrors. So it's very stable. So like this one here that we see, it's a 36-inch blank that we started. So the water jet cutter cut 2 discs and asked that company to make some strips also, about 1.5 inches wide, that I recut myself with the diamond blades, and also sand the end of it with the diamond water sander to make a very smooth surface. And then I have a big pattern made with where the post should be applied in between the plates to make an even structure. That's done at university again. So all the little red dot that you see there is where the post should be. Okay. Next one here. There's a group here. That was the first mirror that we assembled, okay, the 36-inch, so I have some help. Mr. Vien from the university and a friend of mine, François Saint-Martin. In between the plates and the post itself, okay, I needed an interface, because if I were to fuse 2 pieces of glass with posts in between and get it hot enough so it melts and it fuses or welds together, the entire structure will collapse. Okay, if you understand what I'm saying here, is if it's too hot, the entire structure will just melt. So we had to find an interface made of borosilicate with a lower melting point. That's what we found it. So the interface will melt, make the joint, the fusion before the entire structure collapsed. So that was a goal that we achieved.
Kind of like hot melt glue.
Yeah, well, actually, when we assemble it, we use some epoxy to hold not in between the pieces, but around the pieces, so it doesn't do a domino effect here. So what we do is we just apply a drop of epoxy on the side of the post, so it stays there when we apply it there. So it takes about a half an hour, and everything is we can put the top plate on top after. So here's the product before it goes in the oven.
Are all those glass posts the same height?
Yes, they're all the same height, exactly.
What about for very fast optics? Do you all have them already pre-formed?
No.
No?
Excuse me?
Can you repeat the question?
The question was if all the posts had the same length. Yes, they are all the same length because the mirror goes 2 times in the oven. Okay, the first time fuses the piece together, parallel. Okay, there's no different. And then after that, I have a mold, convex mold that I deposit the mirror on it, and I heat up the mold hot enough so the entire structure just slumps on the mold itself. So it doesn't matter the F ratio that you want, F4, F3, F5, I can achieve the same curve, and the top plate will all have the same thickness. Instead of grinding
Yes.
the top, I only have 15 millimeters, I wouldn't have enough material to grind. So by slumping the entire structure, I get the same thickness of the top plate. The only drawback, which is not for me, is that the back of the mirror is convex. Okay, so you have to use a floating cell, which you already use in a telescope that size anyway. And on my grinding table, I have those 54 points all ready to accept that mirror. So here is a 61-inch just fused parallel after the second time in the oven. You see Mr. Vien here is the owner of the mirror. There's 464 posts in between the 2 plates. I'll do one by one. And you will notice that for that size mirror, will be the top plate is double the thickness. So what I did is 3 times in the oven for this one. The first time I just fused 2 plates together to get a 38 millimeters thick top plate, and then I assembled the rest, and then I went on the mold after to do the slump. It's slumped at f3.5, so we've got about 1 inch Sagira in the center. It's quite a bit. There we go, a happy man. Ta-da! So it took me about 6 years to find out that I couldn't get any company to make those blanks. And in my first year of operation with the kiln and the machine, the grinding machine, I've achieved, in not even a year, 61-inch, 50-inch, and 236. In not even a year. So I was able to fuse. So that was the goal that we achieved this year. I was a very, very happy man. Now it came to the aluminum coating. Okay, in the past, again, 3, 4 years, 5 years ago, for smaller mirror, let's say from up to about 24 inches mirror, I had a friend in Quebec, François Saint-Martin, that was doing my coating. This is a system here that you see. But for larger mirror, I had to go in the United States, in Pittsburgh, the company called Fleabag. They were doing up to 3.5 meters, so they were very well equipped. But they closed down last fall, not this fall, but the fall before, in fall 2012. So I had no more place to get my large mirror coated unless I had to ship them in California. So it's kind of expensive first, and it's kind of scary to ship a mirror that size in California and back. So this is the system for 24 inches, and this is my new system that does up to 65 inches. Again, made from scratch. We're going to go through a little bit of the building of the vacuum chamber here. It took about 6 months to assemble and make it work. First, we had some good bases with François. He knows François Saint-Martin had the experience with the smaller chamber they had built. Electrician that worked on it also. We have a very good welder, specialized in high vacuum, and lots of faith. We got the special metal, two dish end metal to make, to make the two sections. Actually, the vacuum chamber is vertical. It's like a shell, one side open, put the mirror in and then close. So that way the mirror is not facing down, which is very scary. When you put a very large mirror on three little stoppers, very scary. And you don't want a mirror sitting face up and the element on the top, or you'll have aluminum will drip on the surface. So here's almost finished here. We got the mechanical pump here, we got a diffusion pump here, all the feed through for the elements and everything inside. We never knew in advance if it was going to work because it's not something that we bought off already made. The good reason was of the price. A vacuum chamber of that size would go for at least $250,000. I couldn't afford that, so for a fraction of the price, we built that one. So here's the front that goes down. So it looks like a big shell. And I have a little video here showing the first mirror made, a 30-inch, made in that vacuum chamber. When we open it, you'll see the mirror inside coated, the first mirror out of the vacuum chamber. Let me tell you that we celebrated. This is not something that you see every corner, a big chamber like that.
I guess you also overcoat?
Yes, we do a SIO overcoat on it, yeah. There it is. Large telescope, anyone now? So now, like I said, I achieved my goal. I'm a one-stop place for a large telescope. I make my own mirror, I make my structure, I coat the mirror and everything, I assemble the entire structure, I can deliver it to your place whenever you want. So it's a one-place stop. This is a 36-inch f3.5 with a folded, I call it the folded Newtonian, Fulham folded Newtonian. I've designed a telescope because that way, I had a group in California asking me for a public telescope, 50 inches diameters, but it would be with a lower eyepiece for security and insurance policy. They didn't want to get the people at 15 feet high in the air at night to observe. It's very dangerous. So they wanted me a system with the eyepiece at least 8.5 feet high for a 50-inch f3.5. And this one here is a 36-inch, and the eyepiece is at 6 feet. So I'll go show you. This is the light path of the folded. So you see that the secondary here is a little lower than usually would be about that high, and the eyepiece would be about here. So I lowered the secondary mirror, make it a little larger with a different angle, and we get the light going outside of the structure, and that's where the eyepiece is. So here's the 50-inch f3.5. It's not completely finished yet. I'm still waiting. The only thing that I don't do on those large telescopes is the secondary mirror, flat. I don't have the technology to do those large flat, so I have a company in California to make them for me. But otherwise, it's all homemade. And the eyepiece, come on.
Do you plan to get around to doing your own flats eventually?
Eventually, yes. Because I have now a Canadian supplier for the very large, very lightweight cellular blanks for large secondary. As an example, I can get like this one, the 50-inch. The secondary is 18 by 19 inches. It's a very small ellipse because of this very small angle. It only weighs 17 pounds versus about 40 pounds for a regular Pyrex. So it's very lightweight. So, but now we have someone in Quebec that does those cellular mirror for us.
When you say a flat, you mean rather than the structure you use with the supports between?
No, it's a cellular. It's like a honeycomb, okay? And it's a flat surface. It's not a convex or concave.
Why can't you do that with your process?
I don't have the technology, the equipment to measure the flatness. I'm specialized in parabolic mirror, and over the years I kept my parabolic experience to that, and I improved my technique. Eventually I would like to make those flat, but it's a new another type of machine to grind and polish them, and a new type of measuring system also. So I'm not there yet, but eventually I will.
But you can do a parabola of any curvature, yeah?
Yes?
So couldn't you just set the curvature to 0?
Yes, but it's a different technique. Sorry?
Repeat the question, please.
The gentleman asked me if I could do a flat because either a convex or a parabolic figure I can make, but to make a flat and measure it, let's say within a tenth of a wave, I don't have the equipment because they are made, those flats are made on very large rotating polishing pad. Okay, the mirror itself runs on the polishing pitch. Okay, instead of me, I'm rolling the mirror with the pitch on top of it. So it's completely different technology that I don't have. Eventually I might build, but right now I don't have.
Norma?
Yes?
When you design the folding part,
Yeah.
how do you judge the trade-off between the size of the secondary and the angle that you need in order to get the eyepiece lower?
Okay, good question. The question is how do I gauge the size of the secondary mirror for that folded design? In the past, I've seen, we call it the Nasmyth system, okay? The Nasmyth telescope is, let's say, a primary mirror. I'm going to go back. Hold on here. Okay, we have the primary mirror, and the secondary is facing, okay, the primary, and you have a tertiary mirror, this angle here that brings the light here, okay, very much lower. The drawback of that system is that the secondary is humongous, about 40 to 45% diameters of the primary. So you lose a lot of contrast, you lose a lot of definition, and it's not the point. I don't like the idea. So that way, the percentage of my system is no bigger than a cast grain at 33%. So it's the same obstruction than a cast grain telescope, but you have it in the folded Newtonian. So you don't get the enlargement, the focal length that you get in the cast grain. You have an f3.5, that's what you get, instead of having an f12. So that's the 50-inch. Here we go. So the creation mode is, I don't like working with computers to design those big telescopes. I like to see, I'm not a, like I say, I'm not a computer geek. I work on large piece of paper. I do the drawing and then I cut the pieces, and that way I know that it's a real size telescope that I'm building, not a small size, and I just take the measurement out. So you have the drawing on the floor, you got all the parts cut at the shop, aluminum parts. You see the altitude bearing is drawn on the floor first, and then I assemble it to make sure everything fits my drawing. So here's the ground board here, and you have the primary mirror cell. Who can say can stand up in this primary mirror, secondary mirror cage here? Right?
Looks like you're scaling up your mechano.
Yes, exactly. You're not the first one telling me that. Because when I was a kid, my grandpa always gave me mechano games. Yes, that's right. So this is the 50 inches, the first assembling of the 50 inch we made, just the rough assembling. But I still make those regular Newtonian telescope also. Don't worry. It's not only the folded Newtonian, and also still make those beautiful wooden telescopes, like 16 inch, like a 10 inches here. This is a 32 inch that is owned by Mr. Doug Cunningham in Bruce Peninsula. He commissioned me 2 years ago to build a telescope, and his wife asked me to build a 10 inch and a 16 inch here for herself. This is a roll-off roof fixed observatory, by the way. I think it's the largest in North America. It's 35 by 32 roll-off. And Mr. Doug Cunningham has made an article on my business that's going to be up in Sky News in March, April issue. I make observatories also on my spare time. So this is a roll-off built in Alexandria, actually, not too far from here. Mr. André Coulombe. Actually, right now he's got a 20-inch telescope in it. Just to show you. This is the 36 inches first light that we did, the first prototype of the folded Newtonian that I made. This is where we did the first light on his land. So like you can see that the eyepiece here is very slow, 6 feet. It's all Servocat Argo-Navis wireless, so everybody knows the system. There we go. 2 feet on the ground on the 36-inch telescope. So thank you very much for your time. And I just wanted to mention, if anyone would be interested to visiting my shop or a group, or I'm always open day, night, weekends. If anybody pass by and wants to visit the shop, you're very welcome. It's not many people that's seen grinding machine working and polishing machine. So thank you very much for your time.
Thanks very much. Appreciate it. We have just 1 second. We have time for about 3 minutes of questions before we have a break.
Yes.
So
Here's my Lotto Max ticket. How much is a 62-inch?
Just the mirror? Just
For the whole scope.
the entire scope?
So the question was, how much is a 62-inch?
About $300,000.
300?
Yeah.
I got 46 million.
But if you look at the Megantic Observatory, which is a 63, okay, it cost about $2 million. So they got a good deal here. Whoops, sorry. Yes?
I'd like to know, how thick are your mirrors?
I keep the ratio 6:1 for a mechanical reason, to make the strongest mechanical structure of the mirror itself, so it doesn't bend under its own weight. That's the ratio that we keep, 6:1.
Okay.
So for 36-inch, you have 6 inches thick.
And what's the ratio of lightness compared to, say, a solid Pyrex mirror?
The lightness, it all depends on the size, okay? Regular Pyrex for what's available on the market, okay, for large mirror, for, let's say, amateur or semi-professional, is either 2 inches, 2¼ inches thick Pyrex. 36-inch diameters will weigh almost 200 pounds.
Right.
Mine only weighed 115. If you look at the 50-inch, a 50-inch usually would weigh about 1,200 pounds or more. Mine's only weighed 320. So you gain a lot on the weight, and also the drawback of the solid blanks is the thermal problem. Okay, you never reach thermal equilibrium on a very large plate.
Okay, so your mirrors cool faster?
Yes, because we blow air in the telescope. There's fan that blow air in between the plates. There's always an air circulation, and the thickest part to cool off is 15 millimeters, not even 3/4 inch.
Okay, 2 more questions. Eric?
Yes.
So how fast can you make the optics right now?
Well, depending on what size.
Okay, so say you wanted to build a 100-inch, and you wanted it to be something like f2. Are you
Okay.
capable of that yet, or?
It's feasible. Yeah, actually,
So the
it's
question
a
again?
goal. You wonder if you can make a 100-inch mirror and how long it would take. Me and the university are working on the design of that mirror right now because the kiln can take it. We have 10 feet inside, so would be able to do it. So it's hard to tell how long it would take. Probably about 2 to 3 months just to make the blank itself, and then another year to grind and polish. Because that 61-inch that you saw there took about 2 months to fuse together, because it's 3 times in the kiln. 3 times the last annealing was pretty long. And the grinding took about 6 months, because even if the shape is already pre-generated, it's still a rough shape. So we have to grind it and smooth it off all down to 3 microns, and then the polishing itself, and then the figuring. So so far we are about 1 year and 4 months on it, and you're not done yet. It's almost finished though. I'm down to about 1 lambda. Yes?
Do you polish other people's mirrors?
Yes, I do.
You do, okay.
Yes, if you go on my website, you will see refiguring mirror or just recoating the mirrors. If you have a bad coating on the mirror, we do the services for the recoating.
So I have sort of one last question, then we'll have to take these questions into the break.
Yep.
Normally, Attila Danko
Yes.
is unfortunately came out with the flu. He sent his regrets. He
Okay,
really wanted to be
that's all
here.
right.
But I'm more curious, when is this 36-inch going to be ready?
Well, his mirror has been done for over a year now. He's got a mirror in his garage for the last year. It's coated and everything. It's the company that makes his structure. It's not me.
Okay.
Well, the story is when he ordered his mirror, I wasn't building the structure. It was at the time that I was looking for a supplier for the blanks. Okay, so he was very patient because 2 years later he didn't have the blank. I didn't have the blank, so he waited for me to get all the technology at the shop to build the mirror. And by the time I was able, he had already ordered the structure to another company in the United States. And now that the mirror is finished, I offered Attila to build a structure, but he already had sent some deposit on the structure, so he couldn't get it back. So I would have been very, very happy to build the structure and the entire scope for him, but it's just a matter of the bad timing.
Well, we're all looking forward to it. Norma, we'll have to end it. Thank you so much
You're
for
welcome.
coming to Montreal.
Thank you.
Okay, everyone, we're going to take a 10-minute break here. As I mentioned, pick up the door prize tickets here. The door prizes are available to anyone. You don't have to be a member. I mentioned earlier that here are some of the benefits in being a member of the RASC. I'll leave this up here. So we'll take a 10-minute break. Okay, so that will be 10 minutes from now. All right. Okay, the next segment is observation reports, and we have a number of observers. So can all the observers, all the people who are sharing their images and photos, please line up here. I'd like to do this segment in 10 minutes, so maybe everyone, you can keep yours to about 2 minutes at most for sharing your images. Okay. So first up is Graham. Graham.
Hello, I guess that's why he told me to stay around the podium then and hand out tickets. Alright, so this was a Star Trail picture that I took up near Cobden. I don't know how long it was, but it was kind of a neat shot. Next one. Oh, going the wrong way.
The other forward.
Alright, this is the Hercules cluster. This one here again was, pretty good. I can't remember anything about this. I took most of these pictures back in 2011. So I've been busy on some new ones, but they're not ready. So, this is the moon. It's what? Oh, it is a little oval. Oh, that's cool. So this is the moon, not necessarily up to dimensions, I guess. It's got stretched. I kind of like this one a little bit because it's got the nice crescent, and you can sort of see, like pointed here, you've got a couple of the craters a little bit more defined. So we go to the next one here. Last month, you remember Eric talking about his nautilus and clouds and how he phoned somebody up and told them all about it and he'd go and take pictures of aurora and all that? Yeah, that was me. So this is my shot. This was about 10 stories up. Sorry, what?
Okay, this is about 10 stories up off the ground from my balcony and looking towards downtown Ottawa. So you can see the noctilucent clouds here, and again, there's some nice little buildings and stuff. This is my best attempt at Saturn. You can see there's a little bit of edge here. What I did on this one is I took a video of it, and then I went and stacked the best images with it, and then I tried to pull as much of the detail out as possible. This was off a relatively small scope. I think this was a 100 millimeter that I'd used. So that's the Skywatcher 100 millimeter. So it's not bad. And then this was over at Nirvana during the summer. This was sort of just point the telescope straight up in the air. and take a picture. I took a couple different ones, some of them with camera lenses and some of them with telescope. And this is sort of, again, the really wide angle view. Don't know exactly where it's pointing.
Lagoon Nebula.
Thank you. So that's this over here?
Yep.
Yeah, okay, that's the Lagoon Nebula. And this is a giant black spot.
The Pipe Nebula.
Awesome. And this over here is?
A Sagittarius star cloud.
Woo! Okay, there you go. I'm like, it looks good. That's what I do. So some good pictures there. And I think that's about it. Oh no, I got this one. This was the supermoon from 2011. Again, it's theoretically a little bit bigger, a little bit brighter. This one here was through the 100mm Skywatcher. It's an ED scope. And, oops, apparently I've got this wrong again. Okay, up here, again, I like this picture because one, it's a supermoon, you get some really good pictures and stuff, but the other thing also is up in the corner here, again, it looks very 3D-ish. You got really nice definition on the what do you call them, craters and stuff. Whereas at the bottom here, it's sort of more blown out, whereas before the other picture was nice on the bottom. And what else I have? I have the transit to Venus. That happened. It was pretty good. This was shot over in Britannia Bay, so there were some clouds that came in near the end. The sun didn't actually just start doing that. And that was just with a Bader filter on my 80mm, not Skywatcher, it was William Optic scope. So that's before, and it just sort of a couple pictures as it went through. And then it went into the horizon here, so that's about it, I think. Somebody else.
Thank you. Thank you. Next up is Eric Romay.
Hi there, everyone. Happy New Year. This okay, so this image is actually the first light that I took with my my Takahashi this summer. I was at Starfest, and actually while I was taking this image, I went over to take a look through Norman Fulham's 36-inch telescope. I asked him to point to this particular object. This is the Cocoon Nebula. And at the time, it was pretty much straight up, so we weren't able to look at it because it would have required stepping onto the top step of a ladder that we kind of decided it was too dangerous to, because the telescope was so big. So in any case, I'm trying to remember exposure times. It was probably about an hour or so for this one. I can't remember that off the top of my head. Where's the? Here we go. This is an image I took of comet Pan-STARRS from the Karp-Diefenbunker. This was back in March of last year when you could almost see this naked eye. It was a pretty bright comet, so a bunch of us got together and tried doing a photo shoot of it. And as you can see, I mean, it was well into twilight in the evening, but you could still see it pretty good. This is the Eagle Nebula that I took using my Explorer Scientific 127mm scope. It's a hydrogen alpha image that I managed to keep all the stars white, but all of the nebulosity, I decided just to color it red. So it's not really an accurate representation in terms of a true color image. As you can see, all the stars are not, they don't have much color in there other than just being white. But so that's a future project of mine I wish to do, is to get the true color of the stars and put it together with this one. This is an hour of exposure. This is one frame in about 400 frames I got, and I didn't have time to process the video to have it ready for tonight, but I've got a video I'll probably be able to show next month that is about 2.5 minutes long, where the auroras just danced across the sky the whole night. Like, it was unbelievable. The whole sky lit up so much that you could actually almost start to read by this light. It casted shadows on me. I've got a couple of frames I took out of the video because they kind of looked silly, but here I was dancing around, in front of it, and it was, silhouetting me against the background and stuff, It was unbelievable. Like, it was past zenith. I've never seen anything like that. Haven't seen anything since. It was October 9th, I think it was, of 2011. Here's the Pelican Nebula. I took this with my Hyperstar lens on my Edge HD 11-inch Smith Cassegrain. This is a total of about 2.3 hours of exposure with my Beta hydrogen alpha filter. I think that's all I have for tonight. Yep.
Thank you, Eric. Awesome. Next up is Janet. Janet, talk.
You can barely see the stars. Happy New Year, everybody. On December 30th of 2013, we were invited to a bonfire party, and I think the temperatures reached like minus 25 that evening. But I wanted to try out my new Bauer 8mm fisheye lens, so I attached it to my Canon, and this is one of the shots that I came up with. It was only about 1 second long with a 3.5 f-stop, but I did manage to get a few stars. They're here, here, and here. I think the next one, you can see them a little better. Yeah. So, well, you can see them on this screen. So that there is, the Orion Nebula is there, and I think, what is up there, Hercules maybe, and yeah, but I didn't know that we were going to be showing the images this large, but I really like the idea of putting together this kind of primitive quality of the bonfire with the dark sky. Thank you.
Thank you, Janet. I wouldn't call that primitive. I think this is beautiful. This is awesome. All right. Then we have Julia. Okay.
On December 11th, I looked at M31, the Andromeda Galaxy. It was really hard to see because it's 2.5 million light years away. It's really, really fuzzy, and it looks like a ball.
That's awesome. Well, thank you, Julia. Hugo.
Yes, we were having a New Year's Eve party at my place, and some people with younger kids wanted to leave a bit early, so I opened up my front door, and I looked up, and I saw this flashing thing up in the sky. It looked like a UFO. If you ever think you might have seen a UFO, that's what it looked like. So I dashed back in and grabbed my camera. But by the time I got my camera, it appeared that the UFO had descended. It's that reddish, funny-looking thing up there, but you can also see some gate lights there, so it's obviously come down. So what it was, and that reminded me of Paul's mystery there last week, or last month, I should say. Now, if you go to the next slide, you can see that the UFO is this Phantom II super stable helicopter drone. And the reason, okay, you say, so what? Okay, the reason I'm showing it is that you wouldn't believe how stable this thing is. In the daytime, my son showed it to me, and it went out of sight. We couldn't find it anymore, it went so high. But he still got control, and you can control it out of sight. It's got such a range depending on what frequency you're using. And he started a business just now using this thing. He's going to be using it in connection with real estate out in the country to map things and so on. So it's got great potential. It's a high definition camera. And if you lose it, if you like, if it goes way up and the battery goes down or something, the signal's weak, the GPS makes it come right back down to where it started. And you wouldn't believe how stable it is. And I didn't realize it had these flashing LEDs up there. So when it's high up in the sky at night, and you can control it. It can go in all different directions, just zip, 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 whatever, and it's totally stable. So if somebody, and there's going to be more of these because people are going to start using them. So there's going to be more UFO sightings, I'm sure. And with that, I introduce Paul, I guess.
Okay, we have an update from Paul Cloninger. Remember the mystery object that he reported on last meeting? Well, here's the update.
Thank you. Now, I may have to update my update. Was your son flying that thing out in the Lanark Highlands at all? Anyway, yes, I do have an update on that for those of you that remember the presentation from last month. I'll just, yeah, if you can run that one, remember our little guy flying around there. This has been a wonderful exercise for me. Oops, I'm doing the same thing. This has been a wonderful exercise for me because, I've been using geometry muscles and trig muscles that I haven't used in a while. And it has generated so much debate. I really want to thank everybody that contributed observations, comments. We had people from Saskatoon Centre, from Winnipeg, all over the place commenting on this thing and coming up with some really, really creative suggestions and ideas. So we did identify it, though. The mystery has been solved, and we had a variety of suggestions before I tell you which one of these it is. But anything from drones, yes, drones, to Chinese lanterns, stratospheric balloons, tethered satellites. This is an image of a tethered satellite taken from the ground. Other satellites, binary asteroids. It generated certainly a lot of discussion. And what I did before Christmas is I contacted actually our next speaker, Mike Earle, given his expertise in satellites, and I asked Mike if he'd be interested in looking at some data that I got, and Mike, if it's satellites, boom, he was right into it and ground some numbers. I don't know how many hours you spent on this, Mike, but I certainly appreciate the effort. I had checked a number of listings of 100 brightest satellites, that type of thing. Couldn't find a match for this, and I still wasn't convinced whether this was an atmospheric object or a space-based object. But Mike, with his perseverance, managed to find an exact match for us. And so yes, the mystery has been solved. It is a satellite. It's not in low Earth orbit. It's in what's called a Millennia orbit. It's a very highly elliptical orbit. Strange properties. I've never seen a satellite move like this, but that's our baby there. It is a Russian communications satellite. It has a perigee of just over 2,400 kilometers and an apogee of about 38,000 kilometers. So very, very elliptical orbit. Orbits in 717.9 minutes, so a very long orbit, very highly inclined, not quite polar, but close to it. It was launched back in 2006, and apparently the Russians reported it as having been struck by orbital debris in 2009. So it is a derelict, just floating away out there, and it matched the orbital parameters exactly there. Mike was kind enough to generate some star charts after he figured out which satellite it was. So you can see from my images there, he generated maps there, and the positions matched perfectly, as well as the times on them. There's its closest approach to M33, and again, you can see the match is pretty good. So I have no doubt in my mind that this is what it is. It is the Russian satellite. Interestingly, the thing that troubled both of us, or that we were still not quite sure about, was this apparent rotation. Because, as I mentioned in the talk last month, if it was a space-based object, if that is one object, it would have to be enormous, much bigger than anything that we've put into space. But as it turns out, it's an illusion. It's a wonderful illusion, just a chance convergence of events and angles that basically, you can see the satellite there. It's got solar panels, but what you're seeing when you see the two objects there is not the solar panels themselves. It is the same object shown twice. It's essentially a double exposure. And as the thing rotated, as the satellite slowly rotates, because the reflections are bouncing off the solar panels, there's a very sharp cutoff. So in the duration of these were all 1 minute exposures that I took, you get times when there's no reflection at all. So you can see this is this motion it's actually the same object, but as it was moving through the frame in the course of 60 seconds, at this point in time, it wasn't reflecting anything back to us. At this point it was, and at that point it was. So some frames showed a double exposure, others, like this one, didn't show a double exposure, but seemed to show some structural content, or at least that's how I had originally interpreted it. But what you're seeing is just the fading level of reflection off the solar panels as the object rotated. So Mike and I had some interesting back and forth discussions about this. And again, thanks for the Christmas present, Mike. I appreciated that. So yeah, so mystery solved. And I have to add, Mike, you know, I rest a lot easier with your identification of this, because I'm much more comfortable with a derelict satellite floating 24,000 kilometers above my head than I am with a drone floating 1,000 meters above my head with a camera. So Hugo, you talk to your sonny. Yeah. So I'm much more comfortable with that. Would have been less comfortable with the drone, and would have been even less comfortable if it had been something much worse. Thank you to everybody that contributed. Oops, sorry.
Okay, thank you everyone for sharing your images and all the preparation you put into it. Next up is Mike Earle with his presentation on estimating two-line elements of low Earth orbit satellites. Thanks, Mike, for coming.
Hey. Thanks a lot, Mike. Okay, I'll get right into it. Not that. So, as you see from Gary earlier, this is a screenshot from the Heavens Above website for the ISS, the International Space Station. Shows the visible passes, and that's not what the talk is about. It's about this below it. That is what's used to generate the passes for satellites from Heavens Above. And the question that I'm going to be answering tonight is, where does it come from? In other words, what this is describing here is the orbit of the satellite itself, the actual the orbital characteristics of the satellite itself. And that is used to generate where it's going to appear in your night sky. Whoops. So, we'll start with this. Before we talk about how an orbit, orbit characteristics are used to generate these predictions, how do we determine the orbit period? So, before we do that, I have to define for you orbit characteristics first. So, the first is orbit size. So, here you see 4 orbits of varying altitudes, 500 kilometers to 2,000, and treat it as a racetrack. We have 4 of them here, and they're all starting in the same place. So now we advance toward our orbit. The green one's ahead, the yellow is behind, and so on and so on. Half the orbit, the green is furthest ahead, so on and so on. And as you keep going, green one wins, of course, the yellow one second, orange one's third, and the red one's fourth. This tells you that the further away the satellite is from the Earth's surface in its orbit, the slower it moves with respect to your location and respect to the Earth's center, actually. Also, the orbit height, some of you might have already seen, that the orbit height can be used to determine how long it takes for the satellite to orbit around the Earth once. Because there's a direct correlation, as you can see, between the speed of the satellite and its distance from the Earth's surface. So if we take a look at the Heavens Above site at the top lines, and you'll see these for every report, that's your altitude of the satellite. So let's say average altitude above the Earth's surface, 417 kilometers. So the orbit radius is the altitude plus the Earth's radius. So about 6,800 kilometers. So again, I said it's directly tied to the period of the orbit, and it is. It's about 93 minutes. You find a lot of the satellites that are low Earth orbit, or between, say, a couple hundred kilometers and about 1,000 kilometers, orbit at about an hour and a half. And so this is about 93 minutes per orbit. So there's also a number, how many orbits per day. So the International Space Station orbits 15.5 times per day. So that means that the astronauts on the International Space Station are seeing 15 sunrises and sunsets a day. So let's take a look at this. Jumble the numbers again. That's called a two-line element set, by the way. Three-line if you count the name as well. Do you see any numbers that matches, whoops, sorry about that. Let's just go backward there. Do you see any numbers that match that one? And I already showed you. There it is right there. So that tells you the number of orbits per day the satellite moves. And it's directly tied in with the distance from the center of the Earth. The size of the orbit, that's one characteristic. There's another one, orientation of the orbit. Here's an orbit about, I think, 1,000 kilometers up above the Earth's surface. There's our horizon in Ottawa. You think we could see it? Probably not. Below the horizon. Everything above that we can see in Ottawa. Everything below it we can't. So if the orbit was 0 degrees, parallel to the equator, and 1,000 kilometers up, we can't see it from Ottawa at all. If you were living on the equator, we go straight overhead, but not in Ottawa. What if it were there? Well, you could just barely see it crest the horizon. What if it were there? Or there? So what I'm describing here is another very important piece called inclination, which is the angle of the orbit plane with respect to the equator of the Earth. So we have size and we have orientation, but that's just half of orientation. There's another half of orientation. So there's your inclination. So if we take a look at, the heavens above again, there's the inclination. We actually mentioned it, 51.7 degrees for the International Space Station. So this is what it looks like. Ottawa can easily see it, obviously, because most of you have seen it. But there's the inclination, 51.7 degrees. So, is there a number in here that matches that? Well, there should be. Hopefully there'll be. There it is right there, 51.65. Rounded up, 51.7. Excellent. So now you have size of the orbit and you have orientation. But like I said before, there's another piece of orientation. Here's our International Space Station, or close to it. And it has an inclination, and it's going in this direction. What if it were there? Same inclination, same angle above the Earth's equator, except it's crossing the equator at a different spot. What about there? Or there? If you're in Ottawa, that makes for very confusing if you don't have that number, that's for sure. It could be anywhere in your sky. And that other piece of the orientation is called ascending node. The reason why they call it that is because the node is the intersection point between the Earth's equator and the orbit of the satellite. And it's ascending, going through that node. That's all it means. So you have size, and now you have orientation. So take a look at this again. The heavens above does not mention that number, so I'll mention it here. It's about 265 degrees, so actually it's right there. And so what this is really saying is, what is the coordinate of the satellite as it crosses the plane, the equatorial plane of the Earth, in right ascension, as seen from the center of the Earth, not from our location on the surface. So can you see a number in there that matches that? Well, yes, there's another one. So what this is doing is just showing you the size and the orientation of the orbit. So say I give you those three then. I give you the height above the Earth's surface, or the size of the orbit, and I give you the orientation. And I tell you, okay, tell me where the satellite's going to be in the future. No one could do it. The most obvious reason, probably, most of you probably figured out already, is that how do you know where the satellite's going to be in the future if you did not know where it was before. If I don't give you an initial position, there's no way you're going to figure out where that satellite is in the future. So there's the fourth number, and then there's the fifth number. Fourth number is where, fifth number is when was it there. You need those numbers. So say I gave you the satellite was here at 9 p.m. January 3rd tonight. Now you have everything you need for a circular orbit to find out where it's going to be in the future. And therefore, you can find out where it's going to be in your sky, when it's going to be over your sky, and where and when to look for it. So those two values I told you about, where the satellite was and the time, that's called mean anomaly and epoch time. They're fancy terms. All they mean is where was the satellite and when was it there. So if we use this as the reference point, the ascending node, as I told you before, and we have an angle from that point, there's your where and there's your when. That's all it's saying. So again, the heavens above does not mention this number. However, it's there, right there. So these are four elements. These are your four elements for a circular orbit that you can use to find out where a satellite's going to be in your local sky. So there's the time. Unfortunately, it's quite vague. A whole day. Remember, this thing orbits 15.5 times a day. So in a two-line element set, there's actually a more accurate time. So what this means is day 354.5388731 of 2013. So day 354 corresponds to the 20th of December. Wow, what a coincidence. So, and that's the actual time. So at that very instant, that's what your characteristics of the orbit are. Where the size, the orientation, where it was, and when it was there. So from there you can go further. That's called propagation. And that's what you see on heavens above. It propagates this to find where it will be in your local sky. There's a lot more math behind it, yes, but these are the basics of what it is. The mean anomaly here is normally measured from a point called perigee, which is actually the closest approach the satellite makes to the surface of the Earth. So let's take a small recap before we go further. So the orbit radius or the orbit size is related to the height, the period, and what's called the mean motion, which is actually number of orbits per day. That's all it's saying. Inclination, that's the first part of the object's orientation. Ascending node is the second part of the object orientation. And we have a where it was, and we have when it was there. So how can we determine these orbit elements? See, I'm turning this on its head now. Before I said we use these elements to determine where the satellite will be. But what if you take a look at a satellite, but you don't know the orbit? This is done every day by the United States, the Air Force Space Command. So I devised a method of determining those four elements from using observations of a satellite that's straight up. That's zenith. It can only be used at the local zenith. You can't use it anywhere else. But there are so many satellites up there, you're going to get one overhead. Or near overhead. So, hey, I'm living in a good time, I have to say. The method works best if the orbit is assumed to be nearly circular. So low Earth orbit, satellites somewhere between 200 and 1,000 kilometers, the orbit can't be very much more than circular. And taking images is a definite plus. I mean, CCD cameras, so on, but I'm going to show you an image that I took with a CCD camera with a camera lens on it. It's no big deal. It works best for low Earth orbiting satellites. The satellites that are ones that are most easily detected in your night sky. So it gives everyone a chance to be able to do this method. So let's take a look at it. Here's your horizon. Here's our location here. Here's the satellite at first, and they're straight up at zenith. So it's going to have an orbit velocity. You can split that up into two pieces. When it's just above the horizon, most of it is called radial. It's heading directly towards you. It's like an airplane. See an airplane taking off very, very far away. It seems to float there, not move. It's moving directly towards you or away from you, so you can't see any motion. But you'll see a very small motion, but you can't detect it with the naked eye very well. But let's take a look when it goes over zenith. The reason why satellites appear to travel so quickly when it's at your local zenith is because all of the velocity is transverse to your eye. It's perpendicular to your eye. There's no away or toward you component of it. And again, when you, so at zenith, these two are nearly the same. So that's the advantage of using the method. They can get rid of a lot of problems mathematically. So, and when a satellite already passes by and is setting in your local horizon, you'll see the same thing heading away from you and down. So you'll see it slow down, and then it'll be very, very slow as it sets. And what you're trying to find first is this, the orbit height. So let's take a look at orbit heights at zenith. So the satellite's traveling at 4 different heights. Notice that they don't really appear to be much different. These are all, say, the same exposure times. From here to here, so on. They're all for the same duration of times. Take a look at the angles as you get further away. This is basically a parallax, you could say. But as you can see, the angle gets smaller and smaller. So that's why the satellites furthest away appear to move most slowly, slowest when over your local zenith.
Mike, can you define parallax?
You're driving in a car, and the closer objects appear to move faster, and the further objects appear to move a lot slower. Oh, I should repeat the question. Define parallax? Yeah, so that's my last answer. Driving in a car, and the objects closer to you, like the street signs, would seem to just whip past you, and the objects much further away from you, like distant mountains or trees, just seem to crawl by. That's parallax. That's basically the parallax effect. And it's not velocity you're looking at, it's angular velocity or angular speed. You're not seeing the velocity is all the same, all the way out. But satellites further away appear to travel more slowly in angle, not in velocity. Velocity is the same. So I published a paper back in 2006 in the journal of the RASC that determined the orbit height using zenith observations of the objects. But I found out soon after that I can expand the method to determine 3 more elements. So take a look at this travel of a satellite over your location on Earth. This is about 45 degrees inclination. Remember, you cannot see a satellite at 0 degrees, a low one anyway, at a 0 degree inclination around the equator from Ottawa. But you can see at 45, and that's the limit where you can see a satellite going through your zenith, is your latitude, 45 degrees, if the inclination is equal to your latitude. Here's 60 degrees, here's 80 degrees, and here's 100 degrees. So it should tell you something. You take a picture, and you know the orientation of the image with respect to your directions on Earth on the horizon. The orientation of the streak will tell you the inclination of the orbit. But let's extend each one of these satellites backwards. What would each one of these lines eventually hit?
The equator.
Exactly. So, what you can also determine there is ascending nodes too. So that's the third one. You have the size of the orbit radius, you have the inclination, and you have the ascending node. And there they are, 4 different ascending nodes. So this is a picture I took of the DumbSat satellite. That is actually the name of it. It's actually a dummy load. They test rocket stages using dummy loads. This is one of them. The local zenith is marked right here for this time, down here. October 3rd at 23:39 UTC. So that's about just before 8 o'clock. Eastern Daylight Time. So there's the picture of the Dumbsat satellite. And it's traveling this way. And so there are your coordinates. You can determine the coordinates with a standard astrometry program. I did this myself with my own method, but I used 3 stars closest to each endpoint. It's the 5-second exposure right here. And there is your angular size of the streak of the satellite. So the satellite appeared to travel in that angle in 5 seconds. And so if you extract all the information, here are your coordinates, right ascension, declination, so on and so on of each. The streak size, divide this by 5 seconds, and this is your, what's called your angular speed. There's your streak orientation, the change in the declination divided by the change in the right ascension. That's all that is. So, oh, who put those in there? Chris, you put those in there? Okay. This is the way to determine all 4. Now, they look mean, but they're not. Anyone in high school, later years in high school, can do these. This is what I call plug and chug, basically. That's what it is. You put the numbers in that you extract from the images that I showed you before, and you get each one of these. Now, there are conditions for each one, but my website will show them, and they're not much difficult. So don't worry about it. Anyone who knows very basic algebra or trigonometry can do this. In fact, they don't even have to know trigonometry. You can do it on a 20-year-old calculator. You can do that. No big deal. So here are the extracted, the ones in bold are all the extracted elements, and here are the actual elements from an actual 2-line element set. Not bad, really, because you're only using 2 observations, streak endpoints. So you can make a 2-line element set yourself, and that can be read by software that can read these. So what does that look like graphically? The red is the one that I determined, and the green is the actual. Not too bad.
Is the offset partly due to the rotation of the Earth
No.
underneath?
No, absolutely not. Because the stars were points in the shot, remember. So, Glenn asked if it was due to the Earth's rotation. No, because the stars were not streaked. This is a method that was made 200 years ago by Carl Friedrich Gauss, who should be up there with Newton and Einstein. And his method you can use anywhere in the sky, zenith or otherwise. But this is my website, and to use it, you need 15 steps. And it's heavy in matrix algebra and high order equations like x to the 8th, x to the 7th, x to the 6th, blah, 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 blah. So when you compare the equations that you saw before with this page, if you look at it, much easier. So is this all? You determine an orbit. Is that all? Absolutely not. This is only initial orbit determination. That's why the orbits didn't match. Determined orbit elements need to be tested by making predictions and then observing the satellite again. Observe the satellite at the predicted locations and make note of the errors between predicted and actual. This is called residuals, those who may have heard the term. You correct the orbit elements until between the error until the predicted and actual are minimized. There are ways to do that, statistical ways of doing it. Gauss invented those too, but they're much more difficult than my method. Make another prediction. Observe the satellite again. It's a repetitive process. There's no such thing as a perfect orbit determination. This can go on forever depending on the accuracy you want. So for educators who want to introduce students to orbit determination and space surveillance in general, I think this method would be far better used than trying to introduce them to Gauss's method, which is absolutely a nightmare to use. It took me about 3 weeks to figure it out. And also step by step from a book. It's not easy. So this is real orbit determination, and have at it, because it's not easy, but you can do it with a pocket calculator and the method I showed you. And you can get the basics of it by doing that. So that is my talk for tonight. Thank you so much for your attention.
I have a question to...
Okay, we only have time for one question,
Okay.
and I apologize for that, but we can have the rest of the questions after the meeting.
Okay.
The reason why I asked about that is because your exposure time in that instance was only 5 seconds.
Yep.
So the stars will just be points.
Mhm.
In the interval between ascending node and where it passed over your zenith, that could
No,
be...
no. You're off there. Because you're talking about an orbit at that epoch time. No, it's not, you don't do that. No. That's not the way it is. The ascending node is based on that orbit at that very moment. It's not when the satellite goes from ascending node to that position.
Right.
No, I understand the question, thank you, but that's not what it is. I should have mentioned that. You do have a good point, though. Thank you.
What is your website?
Yeah, I can mention that too. I'll give you my card. It's Castor2, CASTOR, number 2.ca. I'll be around. Just anyone has any other questions, just let me know. I'll be around. So I love talking about it. So.
Awesome, Mike. Thank you very much. Okay, well, folks, we're going to go about 10 minutes late, but I really want to get this last presentation because it's really interesting. Janet visited Los Angeles recently, and she's got a presentation that is called The Far Side of Hollywood. So with that, Janet Tulling.
Well, now for something completely different. My presentation is a little piece of ancient history compared to some of the things that we've been seeing tonight, some of the presentations. And I think it's important because it's about the vision that one man had about sharing his transformation that happened to him when he was looking through a 60-inch mirror telescope. And from that transformation, it meant that he opened up his wallet and wanted to share this vision with other people. So it's a bit of a good feel story. So earlier this, actually last year, I was going to say earlier this month, we're already into January, in December, I visited the Griffith Observatory in Los Angeles. And there are two separate observatories. There's one on the east wing, which holds a 12-inch Zeiss refracting telescope. And in the eastern dome, this is the western dome over here, there's a colostat, a triple mirrored tracking device, and 3 solar telescopes. Each of the solar telescopes provide a different real-time view of the sun, including sunspots and solar flares. The Griffith Observatory was officially opened as a public educational facility with ownership transferred to the city of Los Angeles on May 14th, 1935. Colonel Griffith Jenkins Griffith, or Griffith J. Griffith, was the donor for both Griffith Park and the observatory. The title colonel is rather questionable because no one really knows if he actually was a colonel or did any time in the military, but nonetheless, he was continued to be called colonel. He was a philanthropist who made his money in Mexican silver mines in the late 1800s and subsequently in Southern California real estate. In December 16th, 1896, he donated approximately 3,015 acres of his personal estate, Rancho Los Felos, to the city of Los Angeles to create a public park on the condition that, quote, the park must be made a place of rest and relaxation for the masses, a resort for the rank and file, for the plain people, end quote. After being profoundly moved by looking through the 60-inch reflecting telescope at nearby Mount Wilson, then the largest in the world, which was circa 1904, a little bit later perhaps, Griffith offered the city of Los Angeles $100,000 for an observatory to be built on the top of Mount Hollywood, to be owned and operated by the City of Los Angeles. The city accepted his gift, but Griffith never saw the completed building, as he died 16 years before it was completed. However, a trust was set up in conjunction with his estate to carry out his will. Griffith was absolutely convinced that any individual, anybody, could gain a more open-minded view on life through observing the sky's distant objects. Reportedly, he said, quote, "If all mankind could look through that telescope," referring to the one at Mount Wilson, "it would change the world." He wanted the plain people, as he called them, to have the same transformational experience he had when looking through the Mount Wilson telescope in nearby Pasadena. The observatory was officially opened as an educational facility owned by the City of Los Angeles on May 14, 1935. It included the Astronomer's Monument, constructed by 6 sculptors 1 year earlier in 1934. Each artist involved was responsible for sculpting one astronomer. One of the artists, George Stanley, was the same person who designed the Oscar statuette for the Academy Awards. The following individuals are represented on the monument: Hipparchus, Nicholas Copernicus, Galileo Galilei, Johann Kepler, Isaac Newton, and William Herschel. But what I really wanted to talk to you about was the latest addition to the observatory, which is the Gottlieb Transit Corridor. This corridor was added when the observatory was refurbished during the years 2002 to 2006. It's an outdoor public solar calendar built onto the west side of the Griffith Observatory. It's 150 feet long, the north-south corridor, and 10 feet wide, the west-east glass-walled passageway. The instrument has 4 primary components. First of all, a meridian line. I don't know if you can see it here. It's a bronze meridian line that runs down the center of the glass-walled corridor. It's bounded on the north by stairs to the lawn and on the south by a large black monolith. The line defines the meridian on the ground, while the walls of the corridor flank the celestial meridian in the sky. The stairs and banister are angled to the north pole of the sky. The meridian arc also demonstrates how the sun changes its elevation along the north-south arc throughout the seasons, reaching the apex of the arc on the winter solstice. The second component of the instrument is this foil piece there. Mounted at an angle on top of the monolith, the foil is a thin, curving metal panel containing a 6-inch long focal length lens. As the sun moves across the sky each day, the lens sharpens the sun's light into a spot that moves across the walls and floors of the corridor. The third component is the median arc here, which is centered at the south end of the corridor, a bronze-faced meridian arc which displays the line and is inscribed with month and day markings, seasonal and lunar indicators, and constellation figures. The arc is 18 feet long and 13 feet high. Each day at local appearance solar noon, as the sun appears to move across the sky, the focus spot of sunlight moves across the meridian on the 7-inch arc, enabling visitors to see how the sun's apparent progress through the sky is linked to our month, day, and seasonal markings on the arc. And here on the left, a guide explains the angle of the Earth's axis in relation to its orbit around the sun, causing the different seasons. And remember, again, this is a fairly basic educational facility. In this slide, we're looking at the sun transiting the 7-inch metal meridian arc. We know that 12 o'clock noon is rarely the exact moment when the sun crosses the observer's north-south meridian line. One contributing factor is because of where the observer is located in relation to the standard north-south meridian lines. As you know, our planet's divided up into 24 standard lines, each 15 degrees longitude apart. In the case of the Griffith Observatory in Los Angeles, it has a longitude of 118.3004 degrees west. That is to say, it is 1.2996 degrees east of the standard meridian, which is at 120 degrees longitude. Since 1 degree equals 4 minutes of time, the Griffith Observatory is approximately 6 minutes ahead of Pacific Standard Time, or has a longitudinal correction of -6 minutes. The city of Los Angeles is -7 minutes PST. However, the reading on my wristwatch at apparent solar noon, when the sunspot hit the middle of the meridian arc at the observatory on December 15th here, was 11:49 a.m. So there was a difference of 11 minutes. So how to explain the difference between my watch time and the 6 minutes the observatory is ahead of standard time was a bit of a puzzle for me. I'm a religious studies scholar, not a scientist, but I went and looked up time and time scales and the sun in the RASC Observer's Handbook, and think I came up with the reason why there was the difference in the 11 minutes. And it has to do with accounting for the drift of apparent solar time, which on that particular day was actually -5 minutes. And so when I added the -5 minutes to my -6 minutes, which accounts for the longitudinal location, I came up with the -11 minutes that my watch showed. So I was proud of myself to figure that out. Now, the final feature, the fourth feature of this transit corridor is an ecliptic chart. On the west side of the transit corridor, a 22-foot long stainless steel engraved star chart illustrates the sun's annual path through the background stars and the constellations they occupy. When sunlight strikes the photoelectric sensors on the meridian arc, the sign activates LEDs embedded in the ecliptic chart and shows the stars of the constellation through which the sun is passing through. And in this case, we can see that it was the 13th constellation of Ficus. The sun in these images is leaving the meridian line, and from edge to edge of the 7-inch meridian arc, it takes the sun only a few minutes to cross it. Unfortunately, I was too busy taking photos to actually time the length of the transit across the arc, but I would say it was somewhere between 3 to 4 minutes at most. As well as this corridor, there are many other interesting features outside and inside the observatory, like this sundial. It was just past 1:30 local time when I took this photograph, and this time the sundial and my watch were in sync. There are also these bronze radio lines on the property which show where the sun sets during the winter and summer solstices and the spring and fall equinoxes. Inside the observatory, there is also a planetarium theater, as well as the Leonard Nimoy Event Horizon Theater, who I heard some people earlier talking about how bad they thought the first Star Trek was. Even if it was bad, Leonard Nimoy nonetheless contributed thousands, perhaps millions of dollars to setting up this particular theater, so he can't be all that bad. But what's interesting is in this theater, the curatorial staff of the observatory hold free public information sessions on the latest astronomical news on the first Friday of every month, so just like us. In addition to the main scopes in the observatories, there are free public telescopes available. Each evening, the observatory is open, and when the skies are clear. And inside, there are numerous exhibitions dedicated to understanding our solar system and universe better. This slide is a compilation of the depths of space haul of what I weigh on some of the better-known celestial bodies of the solar system. As you might notice, my weight on the planet Earth is missing. Though I did step on the scale which calculated my weight on the moon, so I'm sure somebody in here can come up with my earthly weight. One of the many outdoor terraces afforded a great view of the sunset that we had that evening, and I was also able to try out my new 8mm Bauer fisheye lens, which I showed you some images of earlier from the upper terrace of the observatory, and Venus was very prominent in the southwest sky that evening. Finally, I couldn't leave without having a look through the night telescope, even if it was only a 12-inch mirror. Up the upper left here in the frame is the moon, sorry. Go back. Yeah, and I managed to grab this shot of the telescope before the observatory opened to the public at 7 p.m., at which point you could no longer take pictures of it. Because the clouds kept rolling in and out in the evening, the target we could see best when I looked through the refracting scope was the moon. Each viewing there lasts only a few minutes in order to accommodate as many as 600 people every evening, so that in the short time period, all I could see that evening was a blazing moon. I could not see the Chinese U-2 rover, where it landed on the Mare Imbrium on December 14th, which I understand appears as a single pixel in the images from NASA's Lunar Reconnaissance Orbiter. Sorry. Finally, admittedly, the scope is very small by professional standards. It's not a research scope, though. It's a scope to educate the public, and hopefully they, at least some of them, go through the transformational experience that the original philanthropist of the site, Mr. Griffith, hoped that they would go through. So that's my presentation. Thank you.
Thank you, Janet. That was very nice. So I don't know if you folks noticed, but it was obviously quite apparent. Here's Janet. Here she is going on a trip. And in order to make this presentation really, interesting, worthwhile for us, here she is. She basically was at the Griffith Observatory for 12 hours from the transit, okay, or till I shouldn't say 12 hours, till when the sun had set. So that's a real trooper. Thank you, Janet, for doing that. I mean, okay, let's wrap up now. Just a couple of announcements, and then we're done. We mentioned in the last meeting that there's a Ottawa Astronomy Workshop series. It's been running for a couple of months now. And this is open and to everyone. It's free. It's a different format than these meetings here. And what it is a group discussion on a variety of subjects. There's typically one presenter or more presenters that focus on one subject. Lots of Q&A, lots of interaction. Some of the workshops they've had so far on these subjects. The next slide, please. The next workshop is on January the 24th. It's do-it-yourself micro and mini backyard observatory, small, easy, and affordable. Here's the location. Simon Hamner and Rob Lavoie are presenting. If you are planning on attending, could you please send an email to Jim Thompson at that email address you see here. Jim also has on his website the past presentations, okay? They are not currently, he actually does as well stream the presentations like we do on the internet, but they're not currently recorded, but I understand he has plans to record them as well. So next slide. So the library pick of the month, the library book pick of the month is Touring the Universe with Binoculars. Our library, our astronomy library is obviously at the Science Technology Museum, so it's not open right now, but you can pick this up next month if you're interested. Thanks, Estelle. And then just wrapping up here, so next meeting, we will be back at the Science Technology Museum. Good suggestion that came to me earlier this afternoon. It's always a good idea to check the website just in case some surprise comes up that the meeting is canceled, or it won't be canceled, but the meeting is moved, or there's something that's a surprise comes up. We will post a notice on the internet, and of course, as you notice, we'd like to send out a lot of emails too, just to make sure we got everything covered. The one thing I was going to mention at the very last line there is We normally get together after the meetings, and we were thinking, where should we meet? Well, we couldn't make up our minds, so the thinking is that we will meet actually at Kelsey's, which is Saint Laurent and help me somebody, Smythe Road. Okay, so we'll meet there. We'll just drive up the road there. Okay, so ignore that crossed out last line there. We will indeed meet there if you want to have some sort of a post-meeting social.
We usually close the doors at 11, so we only got about like a half an hour.
Oh, is that right? Okay, well, we'll do our best, okay? And next slide. So we had 67 people online coming through the internet, so thanks. I hope you enjoyed it as well. I'm estimating about 85, 90 people in attendance. Great for a cold night, so thank you so much. Please give me some feedback on this, the folks on the internet. What can we do better as well? And is that it? No, there's... next meeting, again, is Friday, February the 8th, Science Technology Museum. And then two subjects so far. Marshall Frank, I saw you here earlier. I'd like to speak to you, actually, if you have a chance. He's got a very interesting subject on Curiosity rover. He has a interest in this, the instrumentation on the rover, some of the findings of the rover, what are the objectives of the mission, and what, and going forward. So that'll be very interesting. And also we have a speaker from Carleton University Library, Monica Ferguson, who is a map specialist, and she has a subject. She has a number of maps of the cosmos that she'll be sharing with us in a brief presentation next month. So I hope you enjoy that. Okay, we're going to close the meeting right now, but we will have the door prizes after the meeting. One last thing I wanted to mention is we have 3 RASC calendars, $16, one for 16. If you're interested, come see me quickly. We're done. Thank you, everyone.
Bye.